In this lecture video, we're going to be looking at applications of the central limit theorem. In the first example, we're going to be looking at the gamma distribution. So let x1, x2, and so forth up to x sub n be a random sample of size n from the gamma distribution with parameters alpha and beta, and let x bar be the mean of the sample, so that x bar is equal to the sum of the x's over n. Denote the common MGF or moment generating function of the x's by cap m sub x, and denote the MGF of x bar by cap m sub x bar. Now it's possible to find the moment generating function of x bar, the sample mean, in terms of the moment generating function of the gamma alpha beta distribution. And I'm using a result here that we really haven't talked about. I'm going to use it here, and I may show you a proof of this in a different video. But for now, let's just take this as given that the moment generating function for the sample mean turns out to be equal to 1 minus beta over n times t raised to the negative n times alpha power. Now, if you think back to the lecture on the gamma distribution, you may recognize this expression, this function, as being in the same form as the moment generating function for the gamma distribution. But now in this case, the parameters for this distribution are not alpha and beta, but n times alpha and beta over n. And in fact, this is the moment generating function for the gamma distribution with parameters n times alpha and beta over n. Now, if you think back to when we first talked about the moment generating function in the section on special expectations in the module on probability and distribution theory, we said that one of the purposes of the moment generating function, one of the uses of the moment generating function, was to generate the raw moments. But the second purpose, the second in terms of what I talked about, but it could be actually first in importance, at least from a theoretical standpoint. But regardless, it's a very, very important use of the moment generating function, is that the moment generating function can help us to identify the distribution of a random variable or a function of a random variable. And this is because let me put it this way, for those distributions for which the moment generating function exists, there is a one-to-one correspondence between a probability distribution and a moment generating function. And so if we are trying to find the distribution of a random variable, and if we know what its moment generating function looks like, and if we can identify or recognize that moment generating function as being the moment generating function of a particular distribution, then we can conclude that the random variable that we're looking at has the distribution that corresponds to that moment generating function. And that is exactly what we're doing here. We have a random variable, x bar, which is a statistic. It's a function of the sample. Its calculation does not depend on any unknown parameters, so it's a statistic. But regardless, it's a random variable, and it has a probability distribution. That probability distribution is its sampling distribution. And what we're after right now is the actual sampling distribution or probability distribution of this random variable, x bar. Now, finding the PDF directly is somewhat complicated, very complicated, especially for a distribution that we're sampling from, like the gamma distribution. But it's relatively easy, as you've seen here, to find the moment generating function for the distribution of x bar. its moment generating function is the same as the moment generating function for the gamma distribution with parameters n times alpha and beta over n. And so what we can conclude then, because of this one-to-one correspondence between probability distributions and moment generating functions, we can conclude that when we're sampling from a gamma distribution with parameters alpha and beta, and if we calculate the sample mean, then the sampling distribution of the sample mean is also has a gamma distribution, but with parameters n times alpha and beta over n. So that's a very interesting and useful piece of information to know. In this case, we actually know the exact sampling distribution for the sample mean. It has this gamma distribution with these parameters. Now, since we know that the sample mean has a gamma distribution with parameters n times alpha and beta over n, and because we know the PDF of the gamma distribution, we can immediately write down the PDF for the sample mean. We know that the PDF for the sample mean in this case is given by x, the argument here, calling the argument x. So x raised to the n times alpha minus 1 times the exponential function evaluated at negative n times x over beta divided by the gamma function evaluated at n times alpha times beta over n raised to the n times alpha power for values of x that are positive. And then this is an indicator function, which is 1 if the statement inside the parentheses is true, and it's 0 otherwise. So this is just kind of a shorthand way of writing a piecewise defined function, which would evaluate to 0 if x was less than or equal to 0. Okay, so this is we know the exact sampling distribution of the sample mean in this particular scenario, and we can express the CDF of the distribution using this integral expression. So and notice that I'm subscripting the PDF and the CDF by n, which is the sample size, because in this context where we're thinking about the central limit theorem, we're going to be thinking about sequences based on the sample size. So increasing sample sizes, and we're going to be thinking about sequences of PDFs evaluated at a particular point, sequences of CDFs evaluated at a particular point. And so this the CDF for a given sample size, a given value of n, the CDF of x bar would just be the integral of the PDF from 0 up to x. Okay, and so we can actually, because we know this PDF, and we can approximate the CDF, we can graph these functions. And for example, SAS has the gamma PDF and the gamma CDF built in. All we have to do is supply the arguments, and then it also tell it where we want to, at what point or points we want to evaluate those functions. And so I've created plots of the PDF and CDF of the sampling distribution of x bar for various sample sizes. And I've included them all on one slide so that we can compare them. And so this plot shows the PDFs of the sampling distribution of the sample mean in random samples of size n from the gamma distribution with alpha equal to 1 and beta equal to 1. So I had to pick some particular gamma distribution to start off with, right? If we're going to look at a concrete example of a particular gamma distribution, we have to use particular values for alpha and beta. And so I just used alpha equal to 1 and beta equal to 1. Now, these different graphs correspond to the PDF of the sample mean for various sample sizes, starting at 2 and going up to 100. Now, this black curve here, this corresponds to, this is the PDF of the sampling distribution of the sample mean from a gamma distribution with parameters alpha equal to 1 and beta equal to 1 when the sample size is 2. And so you can see that this distribution is very highly right skewed. It's not symmetric at all. It's got a long skinny tail to the right, and it is therefore right skewed. Now, if we increase the sample size to 5, then we get the red curve. And so we can see that it is still very right skewed, but it's not as right skewed as when the sample size was 2. If we increase the sample size further to 10, we get the blue curve. And again, it's still skewed to the right, but it's not as skewed as either the red or the black curves corresponding to sample sizes of 5 and 2. Continuing to increase the sample sizes from 10 to 20, from 20 to 30, and so forth, we're seeing that the distribution, the PDF, is becoming less and less and less skewed. It's becoming more, or at least closer and closer to being symmetric. When we look at the sample, the graph for sample size of, let's say, 50, it's really becoming difficult to detect a skewness, at least visually. For samples of size 70, the purple curve, all right, it looks fairly symmetric, although we know that it has some skewness still. And then the final curve for samples of size 100, you know, if all we had on the graph was this gray PDF corresponding to a sample size of 100, I think it would be fairly difficult for us to see visually that there is positive skewness there. But because it's a gamma distribution, we know that there is right skewness. Gamma distributions are always right skewed, regardless of parameters. Okay, they will always be right skewed, but what we're seeing here is that as we increase the sample size, the sampling distribution of the sample mean, when sampling from this particular gamma distribution with parameters alpha equal to 1 and beta equal to 1, as the sample size increases, the sampling distribution of the sample mean becomes less and less and less skewed. Now here is the corresponding plot of the CDFs, which is perhaps a little bit less useful to us at this point. We'll have some similar plots of CDFs, but we'll be comparing them to the CDFs of the standard normal distribution subsequently. Okay, now let's go back to considering sampling from the general gamma alpha beta distribution. And we want to think about what are the parameters, what are the mean and variance? What are the mean and variance of the sampling distribution of the sample mean when we're sampling from this general gamma alpha beta distribution? And so denote the mean and variance of the sampling distribution of x bar in the usual way, so mu sub x bar and sigma squared sub x bar. Then it can be shown that the mean and variance of the sampling distribution of x bar are alpha times beta and alpha times beta squared over n. Okay, and so anyway, what we're going to use these values subsequently when we look at the application of the central limit theorem to this situation. If the variance of the sampling distribution of x bar is is alpha beta squared over n, then the standard deviation of the distribution would be the square root of that. Okay. Now we're going to think about applying the central limit theorem to this situation. And you'll remember that the central limit theorem is a statement about convergence of the CDF. And so we need to, well, the CDF of the standardized random variable in particular. And so let's first standardize the sample mean. And so we will let Z sub n be the standardized version of the sample mean. Remember that when we say we're going to standardize a random variable, what we're going to do is we're going to subtract off the mean of its sampling distribution and divide that difference by its standard error, or in other words, the standard deviation of its sampling distribution. And so Z sub n, and again, I'm subscripting Z with n, right, as an index of sample size. And so the standardized version of x bar, Z sub n, is equal to x bar minus alpha times beta, which is the mean of the sampling distribution of x bar, divided by the square root of alpha times beta squared over n, which again, that denominator is the standard error of x bar. So Z sub n is the standardized version of x bar. It's a random variable, therefore it has a distribution, and associated with that distribution there is a CDF. And so let's denote the CDF of Z sub n by H sub n, and we'll denote the argument to that CDF by Z, lowercase z. Now this notation, H sub n, is consistent with the notation that we used in talking about the central limit theorem in general. Okay, and so now let's think about the actual expression, if we can come up with it, the true sampling distribution of Z sub n. Okay, so so the CDF of Z sub n. So again, for a given value of Z, and by the way, we will be thinking in terms of the continuity points of this distribution, because this is a continuous distribution and there are no jump points or anything. Every point every point on the real line is a continuity point for this distribution. Okay, so let's consider a real number Z, and let's consider evaluating the CDF of Z sub n at Z. And so by definition, this is the probability that the standardized version of x bar, Z sub n, is less than or equal to the argument, little z, at which we are evaluating that its CDF. And because Z sub n is equal to this standardized version of x bar, we can replace Z sub n by this expression. So this would be the probability. This probability right here, this first one, would be the probability that Z sub n is less than or equal to little z is equal to the probability that x bar minus alpha beta over the square root of alpha beta squared over n is less than or equal to little z. And then we can use some algebra and rearrange things inside the parentheses to get a probability statement involving x bar by itself. Okay, now you'll recognize that this probability statement here is just the CDF of x bar evaluated at alpha times beta plus z times the square root of alpha beta squared over n. Now the CDF of x bar is denoted by cap g sub n, and so we evaluate that CDF at this point, this value, this expression, and so that is just given by this integral from 0 up to the argument alpha beta plus z times the square root of alpha beta squared over n, and we're integrating the PDF of x bar. So this is the PDF of x bar that we found, or wrote down, typed in on a previous slide. So that's a fairly complicated looking integral. I'm not sure that I want to integrate that. You may not want to have to fool with that either. But this, what we're finding, the point here is that we are able to find the CDF, the true CDF of the standardized version of X bar. Because we know its true sampling distribution, we're able to find the CDF of the standardized version of X bar, and it's given by this expression. So this expression for H sub n is indeed difficult to compute. Now, however, by the central limit theorem, we know that at any given real number z, and again, technically we would say at every continuity point of H sub n, but because this is a continuous distribution without any breaks, every point is a continuity point. So at every real number z, the CDF of z sub n converges to the value of the standard normal CDF at that same value of z as the sample size increases. So what that means is that if we think about this graphically, what this is telling us is if we consider a sequence of graphs of H sub n as a function of z, then as the sample size increases, the graph of that the graph of H sub n is going to look more and more and more like the CDF of a standard normal random variable as the sample size increases. And so what this means then, because we use CDFs to get probabilities, or at least we can, what this means is that for sufficiently large samples, the CDF of z sub n can be approximated by the standard normal CDF, and we could therefore use the standard normal CDF to obtain approximate probabilities for or involving the random variable z sub n. Okay, but again, what this is telling us is that for sufficiently large sample sizes, this integral right here, which is the expression, the integral expression for the true sampling distribution of z sub n, which again is the standardized version of X bar, for sufficiently large samples is approximately equal to the standard normal CDF evaluated at z. Now, this is kind of an amazing thing, I think, because if you were to look at the integral expression for the standard normal CDF, the integrand does not look anything like the integrand in this integral. And yet, what the central limit theorem is telling us is that this complicated looking integral can be well approximated by the standard normal CDF evaluated at z. Now, in order to get an idea of the quality of this approximation and how it improves with increasing sample size, I've created some graphs, some slides, a sequence of slides showing plots of the CDF of, also plotting H sub n and the standard normal CDF for various sample sizes. So this helps us to get an idea of for this situation, what does sufficiently large mean? And so for samples of size 2, here I've got a graph of the blue curve is the actual CDF of z sub n. The blue curve is H sub n, right? So the blue curve is is a plot of this function as a function of z. So I'm using SAS to evaluate this integral here, and then plotting that graph, and that's the blue curve. The red curve is the standard normal CDF. And so what the central limit theorem is telling us, this application of the central limit theorem, is that as the sample size increases, the blue curve represented, or which it represents H sub n, and the red curve, which represents cap phi, should look closer and closer and closer together. Okay, so for samples of size 2, at a particular point, are the two functions close to each other? Well, it depends, doesn't it? For some values of z, here I've got labeled x, but for some values here on the horizontal axis, the points are close, but for other points, for example here, they're not that close. Okay, but again, the sample size is only 2 here. Let's increase it to 5. So from 2 to 5, we see an improvement. Let's increase it to 10. Okay, so from 5 to 10, we're getting further improvement. For samples of size 20, now we're getting pretty close, pretty doggone close agreement. All right, and so again, what we're wanting to be able to do here is to, instead of using the blue curve in calculations, because coming up with values for the blue curve, coming up for values of h sub n can be very difficult. We would rather use the red curve because that's easier, because we have, for example, the standard normal table. So the question is, would you be comfortable using the red curve to approximate the blue curve for samples of size, well, 5? Probably not. How about if the sample size was 10? Are those two curves close enough together that you would be comfortable using the red curve to approximate the blue curve? Well, it's better than sample size of 5, but it's still not that great. For samples of size 20, that's getting pretty good, pretty close. For samples of size 30, the graphs are almost indistinguishable. For samples of size 50, there's even less daylight between the two curves. And for samples of size 100, there's very, very good overlap. The red curve is an extremely good approximation to the blue curve. And so what sample size would you be comfortable with? I know that I would be comfortable using the red curve for a sample size if the sample size was 100. If the sample size was 50, I'd still be okay. Samples of size 30, yeah, I'd be willing to use the red curve instead of the blue curve. I might even be willing to use the red curve as an approximation to the blue curve for samples of size 20. Now, I wouldn't want to go any lower than that, okay, but probably at least 20 would be satisfactory. Okay, now we can find the PDF of z sub n by differentiating the CDF. So we've been plotting the CDF of z sub n, but we can also find the PDF and we can plot that. So the PDF of z sub n is given by the derivative of the CDF, okay, and it's expressed here. And so now what we're going to do, I've got a sequence of slides showing plots of the PDF of z sub n along with plots of the standard normal distribution, and we can again see how well the standard normal PDF approximates the PDF of z sub n, which is the true distribution of the standardized version of x bar. Okay, so again, the blue curve is the actual PDF of z sub n for a given sample size, and the red curve is the standard normal. All right, so we can see here that for samples of size 2, the red curve is not a very good approximation to the blue curve at all. If we increase to a sample size of 5, we see that the approximation improves. We see that the blue curve is getting closer to the red curve. If we increase the sample size to 10, there's even more improvement. For samples of size 20, all right, it's getting closer. For samples of size 30, even closer. Samples of size 50, and sample size of 100. And so you can see that as the sample size increases, the PDF of z sub n, which again is the standardized version of x bar, gets closer and closer to the PDF of the standard normal distribution. Now, let me just remind you that the central limit theorem is a statement not about PDFs. It's a statement about convergence of CDFs. Okay, so that's why we looked at convergence of the CDFs first. That's why we looked at convergence of these graphs first. But that does translate into convergence of the PDFs in some sense. And so that's why we're looking at that as well. Because when we think about, it's easier for us to see visually convergence to the standard normal PDF than to the standard normal CDF, because we know what that standard normal PDF looks like. It's that nice bell-shaped curve. Okay, so that's why I'm showing this. So you're seeing the central limit effect, central limit theorem effect. As the sample size increases, the distribution of Z sub n looks more and more like the standard normal distribution, whether we're looking at the CDF or the PDF. Now, the other point that I would make, and the other reminder that I would give you, is that the central limit theorem is a statement, technically it's a statement about convergence of the distribution of the standardized version of X bar. Okay, but I can also, this also translates into a convergence of the distribution of X bar itself. And so now let's look at this. Let's look at the CDF of X bar itself, G sub n, which can be expressed in terms of the standardized, or the CDF of the standardized version of X bar. So G sub n can be expressed in terms of H sub n in the following way. Okay, and we don't really need to get caught up in the details. I'm just showing you how I calculated this, because then I'm going to graph the CDF and the PDF of X bar and show and compare that to the corresponding CDF and PDF of the normal, of a corresponding normal. Now, in that context, we're not going to be comparing to the standard normal. We're going to be comparing to the normal that has the same mean and variance as the distribution of X bar. And you'll remember that the distribution of X bar, the mean and variance, well, in particular the variance of the distribution of X bar depends on n. Remember that the variance of X bar, when sampling from a gamma alpha beta distribution, is alpha times beta squared over n. So as n increases, as the sample size increases, the variance of the distribution of X bar is decreasing. And so when we compare the graphs of the CDF and the PDF of X bar to a corresponding normal distribution, we have to adjust the variance of the distribution in each case. Now, this slide is showing that because the CDF of the standardized version of X bar, the CDF of Z sub n, is approximated by the standard normal CDF for sufficiently large n, the CDF of the sampling distribution of X bar itself can be approximated in the following way. So this expression here, again, is the integral expression for the CDF of X bar itself. All right, so that is given by the CDF of X bar evaluated at a value x, right? So notice that x is the upper limit of integration here. And this is exactly equal to, or can be expressed in terms of, the CDF of the standardized version of X bar, Z sub n, so expressed in terms of H sub n in this way. And by virtue of this central limit theorem, the sampling distribution, let me back up, the CDF H sub n evaluated at this point is approximately equal to the CDF of the standard normal distribution evaluated at that point. So the approximation we're approximating G sub n evaluated at x by the standard normal distribution evaluated at this point. And this is, so I was talking about having to make an adjustment to account for the decreasing variance, and that is taken into account here. Okay, so the following slides show the actual CDF of the sampling distribution of X bar along with the CDF of the approximating normal distribution. So the approximating normal distribution, again, I will be, the approximating normal distribution has the same mean and the same variance as x bar. And so again, the blue curve is the actual CDF of x bar, and then the red curve is the CDF of the corresponding approximating normal distribution. And so here, this is for a sample size of 1, okay, and then for a sample size of 2. And you're going to see that as we increase the sample size, so here we have a sample size of 5, a sample size of 10, a sample size of 20, 30, 40, or I'm sorry, 30, 50, and then 100. And so you can see that as we increase the sample size, then the corresponding normal distribution, well, let me put it this way. So the true sampling distribution of x bar, the true CDF of x bar, becomes closer and closer to the corresponding normal distribution, the normal that has the same mean and variance as x bar itself. And so again, when the sample size is 20, there's very good agreement between the two functions. The agreement's even better for samples of size 30, 50, and then 100. And as previously stated, the PDF of the sampling distribution of x bar is given by this expression here. The PDF of the approximating normal distribution would be given by this expression, all right, where cat phi, or I'm sorry, this is lowercase phi, is the PDF of the standard normal distribution. So we would be evaluating the PDF of the standard normal distribution at this expression here, all right, and pre-multiplying by that. And that would give us then the PDF of the approximating normal distribution, or in other words, the normal distribution that has the same mean and variance as x bar itself. And so here we're comparing not the CDFs, but we're comparing the PDFs of the actual, so the actual PDF of x bar for a given sample size, and then the corresponding approximating normal PDF. So again, here we have n equal to 1. And so this is the blue curve for samples of size 1. This is actually just the parent distribution that we're sampling from for this situation. This is the PDF for the gamma distribution with parameter alpha equal to 1 and beta equal to 1. Now, as we increase the sample size to 2, and then 5, and 10, 20, 30, 50, and 100, you see the central limit theorem effect on the distribution, on the PDF of x bar itself. Even though we're sampling from a very skewed distribution, again, this is for samples of size 1, all right? So this blue curve, this is the distribution we're sampling from. It's a very right-skewed distribution. Even though we are sampling from a very right-skewed distribution, as we increase the sample size, the sampling distribution of x bar, the blue curve, looks more and more like the PDF of a normal distribution, which is the red curve. And so by the time you get to a sample of size 100, you really can't tell the difference. Even for samples of size 30, there's very good agreement between the two PDFs. And I would go so far as to say that even for samples of size 20, the agreement's okay. And if we go back to plotting the CDFs, if you remember, the CDFs are, where we would get probabilities. I would say that, the agreement here, by looking at the CDF for samples of size 20, I would be comfortable approximating the true sampling distribution of x bar using the corresponding normal, even for samples of size 20. Okay, and so based on the graphs, when sampling from a gamma distribution with parameters alpha equal to 1 and beta equal to 1, as we've been doing in these graphs, I had this question for you. what sample size appears to be sufficiently large for the normal approximation to provide an adequate approximation to the true sampling distribution of the sample mean? Would you be satisfied with a sample size of 10 or 20, 30, 50, and 100? You know, you have to make that decision. But the point I'm making here, and I think that this example does a pretty good job of this, again, showing that even when we're sampling from a very highly right-skewed distribution, and this would apply if we were sampling from a distribution that's skewed to the left, but even when we're sampling from a very highly skewed distribution, the effect of averaging, right? Averaging the values from in the sample that we've obtained from this this skewed distribution, the effect of averaging decreases the skewness of the distribution of the sample mean, so that the actual distribution of the sample mean looks more and more like a normal distribution. So we're going to look at another example as well, but this video is getting a little bit long, and so I'm going to stop this video, and we'll pick up the next example in the next lecture video.